Well, hello, everyone. My name is Roy Levy. I'm a faculty member in the Department of Psychology and in the School of Social and Family Dynamics at Arizona State University. A little bit about me. I am a quantitative methodologist. Most of my work is involved in things like psychometrics and latent variable models, and in particular, Bayesian approaches to those types of models and designs and analyses. Much of my background is in educational measurement and psychological measurement. That's a little bit distinct from what I think most folks here have as their background, but there's certainly a lot of connections and parallels. So in some of my presentation of things, you might see overtures of more of an educational measurement orientation, but the same ideas hold across. And what I'd like to do in the time that I have today is go over some ideas surrounding Bayesian inference, ultimately getting to why might it be useful for us? Why Bayesian inference for measurement modeling? But even before that, why Bayesian inference? And even before that, what is Bayesian inference? I think for some of us, we might be less familiar with it. For others of us, we might be more. I don't think we'll get into some of the 3 beer questions that were just posed in this morning, but I'm excited to get into them later on when time permits. But to get started, here's a quote I like from Dennis Lindley about what Bayesian statistics is about. Bayesian statistics is not a branch of statistics. It's a way of looking at the whole of statistics. So if your experience is like mine, this is not something that you were taught throughout your quantitative methods training. It might have been mentioned as a special topic or a seminar or something like that. And indeed, that's how it seems to be taught for the most part, at least in the programs I'm familiar with. But really, we could be doing everything in quantitative methods using Bayesian statistics. So to get started, I want to use a little example that I've taken from the work of Gerd Gigerenzer and colleagues on medical diagnosis. So here's the setup that Gigerenzer poses. Consider women in a particular age range with no family history of cancer and no symptoms of cancer. The proportion of such people that have breast cancer is 0.008. We have a mammogram screening instrument intended to detect the presence of cancer. If the patient has breast cancer, the probability of a positive mammogram that is indicating cancer is present, 0.90. If the patient does not have breast cancer, there's still some chance of a positive result on the screener indicating cancer is present. That's 0.07. All right, we have the patient, they undergo the mammogram screener, the result is positive. What should we infer? And if you're like me and like most people, this is not something that's easily done in your head. There are ways to make it easier. And one of the ways to make it easier is to work instead of with probabilities with what are called natural frequencies. Counts, whole numbers, not tiny decimals. So here's the same problem framed in terms of natural frequencies or counts. So think about a group of 1,000 of these people in this population, same age, no family history. 8 of those 1,000 people actually will have breast cancer. We have the mammogram screening. Of the 8 that actually do have cancer, 7 will have a positive mammogram result indicating cancer is present. Of the 992 who do not have breast cancer, 69 will have a positive mammogram result. Okay, we have a patient. They undergo the screener, result is positive. What should we think? What should we infer? Well, one way to tackle this is with something like a tree diagram. So starting at the top, we have this pool or population of 1,000 women. Working towards the left, 8 of them actually do have breast cancer. Of those 8, 7 of them would test positive on the mammogram screener, 1 of them would not. Of the 992 who do not have breast cancer, 69 of them would test positive, 923 would not. We have a patient, take the mammogram screener, the result is positive. What should we infer? Well, just thinking about this in terms of probabilities, what's the probability that this patient has breast cancer given that the result of the mammogram is positive? Well, just looking off the tree, let's see. We got 7 people way over there on the left. Those are the people that have a positive mammogram result and actually do have breast cancer. Out of how many total people have a positive mammogram result? Those 7 plus these 69 who actually don't have breast cancer, 7 out of that total, 7 plus 69 to 76, rounding to 2 decimal places is 0.09. We'd say on the basis of sort of reasoning through this tree, the probability that a patient who has a positive mammogram screener actually has breast cancer is about 0.09. That actually is an instance of Bayes' theorem. It's Bayes by tree. We can formalize this with more things like expressions and equations, and that's what Bayes' theorem really does for us. Here's our setup. To keep it simple, there are 2 entities, X standing generically for data, things we've observed, and theta standing for a parameter, something we haven't observed. We know some things. We know the probability of data given the parameters. The expression there is P, X, vertical bar, or conditional on theta. That tells us what we should think about the data if by some way we were to know the values for the parameters. Inference proceeds in the opposite direction. When we learn the value of the data, the things that are actually observable, what should we now think or believe about the unknown parameters? Bayes' theorem really different things, 2 of which are really important. The first one is the conditional probabilities for the data given the parameters. That's sometimes referred to as the likelihood function for the parameters. That's what's in red. I try to use red to stand for anything to do with conditional probability of data. Another thing that's important, the previous probabilities for the unknown parameters, that's the term in blue. And then the thing that's actually less important, at least in modern computation schemes, is in green, the probability for the data all by itself without reference to the parameters. Those show up on the right-hand side of the expression for Bayes' theorem. We'll get to the left-hand side in a minute, but just to make it concrete with our example, on the right-hand side, in red, the conditional probability of observing the mammogram result given whether or not the patient has breast cancer. In blue, the previous probability before we observed the mammogram that we thought the patient had breast cancer. Those are the 2 important things in the numerator that are combined. That's where we're going to spend most of our time and energy. What shows up on the left-hand side, as we'll say more about, is our solution, our answer. It's the posterior probability for the unknown parameters given the data. Posterior meaning after having observed the data in X. Okay. So let's do this. Let's go through each of these terms and let's see this in the context of our little medical diagnosis example first. The term in red, conditional probability of the data given the parameter. This is also our likelihood function. So once we have our observed data, this tells us something about the value of the parameters. In the medical diagnosis example, we were given this information. We were told if a patient has breast cancer, the probability of a positive mammogram result is 0.90. So at the top there, I've just written as an expression, the probability of a mammogram result being positive, given that breast cancer, yes, is present, is 0.90. Which means if breast cancer is there, the probability that the mammogram result is negative has to be 0.10 because they got to add up to 1. I tend to look at this in things like a table. Here's a conditional probability table down there at the bottom where the rows correspond to the different values for the parameter. The first row there is what if, yes, breast cancer is present, and the values in the first row say what's the probability of a positive or negative mammogram result. There's the 0.9 and 0.10. We were also told that if the woman does not have breast cancer, there's a probability of a positive mammogram result is 0.07. So if breast cancer is not present, there's still a probability of a positive mammogram result 0.07, which means the probability of a negative result's got to be 0.93 because they got to add up to 1. And that's what forms the second row of this table. We saw this term in the tree. If we look at the tree diagram, the conditional probabilities correspond to particular portions of the tree. The first row of the conditional probability table says of the people that have breast cancer, the probability of someone having a positive mammogram result is 0.9. That's roughly speaking, that's 7 out of 8 people in our pool of patients. And then over here, The second row of the table, well, if somebody does not have cancer, there's still a 0.07 probability of the mammogram result being positive. Roughly, that's the 69 of the 992 who do not have breast cancer. These things were lurking in the tree the whole time. The term that I tend to put in blue is the prior distribution. This is the prior probability distribution for the unknown parameter. It captures what we think about the parameter before observing this data at hand that we're about to synthesize or incorporate. We were told some information as well that's relevant from our problem. So before seeing anything from the mammogram result, we know that the proportion of people in this age range with no symptoms and no family history that actually have breast cancer is 0.008. That's information that I can use to assign a prior distribution. Before seeing anything else, before observing the mammogram result, what do I think the probability that this patient has cancer? 0.008. Probability that they do not, 0.992. That too is part of the tree diagram. It's the top portion. We said of the 1,000 women in this pool of people, 8 of them do have cancer, 992 do not. That corresponds to the prior belief, well, 8 out of these 1,000 will have cancer. Those are the two terms in the numerator. That's where really the action is. The denominator there on the right-hand side is the marginal probability for the data that we observe marginalizing over the parameter. There's a little formula. We'll step through the calculation. But what I want to highlight is what this term does and does not do. What it does is normalize the distribution. It makes sure the probabilities are legit. Make sure they add up to 1. Right? Probabilities go between 0 and 1, and the probability of all the different possibilities ought to add up to 1. So all this term in the denominator does is put things in the proper probability scale between 0 and 1, making sure everything sums to 1. If you look in the notation, just p parentheses x, theta is not there. So this does not speak to anything about the parameter. It's really just a feature of the data. In more complex Bayesian models, we will not even bother with this term, but for the sake of going through this example, it's worthwhile to show the computation and see what role it plays. So there's the formula there at the top, and I'm going to step through it. It says, okay, to get that marginal probability for x, I need to look at the, let's see, that says the conditional probability for x given theta. That was the first table there in red, and then multiply by the probability for theta. That's the table in blue, and then do some adding. So I'm just going to multiply across. The 0.90 times the 0.008 is 0.00720, teeny tiny numbers. 0.07 times 0.992 is 0.06944. And then those two numbers added together, 0.00720, 0.06944, those sum up to some number, 0.07664. Okay, that's what this result is. Marginally, that is averaging over the status of breast cancer. The probability of a positive mammogram result is 0.07664. Doesn't mean much to me, but it is lurking there in the tree as well. It's the total, what's the probability of seeing a mammogram result that's positive regardless of breast cancer status? It's those 7 patients who actually do have breast cancer and those 69 who don't out of the total of 1,000. So if I form these terms on the right-hand side, do the multiplication in the numerator, do the division by this thing in the denominator that we just calculated, what Bayes' theorem spits out on the left-hand side is this term, the posterior probability distribution. And I tend to use purple font for anything having to do with posterior probability distribution. The red, the blue, the purple helps me keep things straight. I find it useful for instruction, but if it doesn't mean anything to you, ignore it. The posterior probability distribution is our answer. It reflects what we now think about the unknown parameter, given that we have observed and incorporated the information from this data. All right, so let me just finish out this calculation here. Looking at the numerator, it says, okay, take the observed value for the data. We observed the mammogram was positive, so I'm using that first column there, the 0.90 and the 0.07. Multiply that by breast cancer prior probability, 0.008 and the 0.992. Hey, we just did that multiplication, getting this table all the way on the right. That's the numerator, 0.00720 and 0.06944. Bayes' theorem says divide that by the sum of those two. Yep, that's by the 0.07664. So, okay, deep breath. 0.00720 divided by 0.07664 makes me to a value of 0.09, rounding to 2 decimal places. 0.06944 divided by 0.07664 takes me to a value of 0.91, rounding to 2 decimal places. This is now on the probability scale. Everything adds up to 1. And I would reach the conclusion that the posterior probability that this patient has breast cancer is 0.09. The probability that they do not, 0.91. See a bunch of nodding heads. So we've seen sort of this thing before, but this might be a good time if we accept. Yeah.
I mean, this might venture into the 3-year philosophy.
Yeah.
But if we're talking about a specific woman.
Oh, okay. I'll repeat things as well too.
This is Ryan Andrews, Boston University. So this might venture into the 3-year philosophy discussion, but for a particular woman, the way that you phrased this, a woman either has breast cancer or doesn't. So the probability is either 1 or 0. So I'm not sure how this avoids the same criticism that people throw at frequentist statistics, where they say, you know, it either does or doesn't happen. I don't know what a 0.09 probability means when I'm talking about a specific woman. So are you talking on averages, or how do you interpret that?
Great. Let me try to quickly restate that, but of course, if I get it wrong, please correct me. So the thrust of the question was the patient either has breast, in our simplified version of this story, patient either has breast cancer or does not. So the probability is either a 1 or a 0 in some sense that they have breast cancer. What does it mean to say the probability is, in this case, 0.09? How can that have meaning? Are we talking about averages over a group of such patients or something like that? I think the answer to that question is indeed the same kind of thing that came up in the what is probability. The way that I use the language of probability is as an expression of uncertainty. The framing as you have it, the patient either does have cancer or does not. The probability is either a 1 or a 0. I would associate that with more of a frequentist interpretation of probability. I want to keep that distinct from frequentist inference and Bayesian inference. I'm really talking about the interpretation of probability. I am quite content to talk probabilistic or to express my beliefs probabilistically about events that either are or are not, have or have not happened, or one-off events that don't require some long-run repeated set of observations, like a frequentist interpretation of probability does. Historically, these views of probability, that it's an expression of belief or uncertainty, have been associated with Bayesian inference. That's how I sort of identify myself. That's how I use the language of probability. But it's not actually necessary to conduct Bayesian inference. There's a deeper answer that is probably a 3-beer answer, but to me, it's quite natural to use probabilities as expressions of uncertainty, even about one-off events. We do this all the time in our everyday language. It's only when we get into stats class that somebody tells us there has to be some long-run relative frequency that stabilizes in order to speak meaningfully about probability. So I hope that helped kind of get at things, but happy to follow up if we discuss more.
Hi, I'm Jennifer Manley. I'm in the back here. Your presentation was incredibly clear, and that's why you have so many nods. You're going to have to deal with me, though, which is I really don't understand why we're doing this. How
Sure.
is what you're describing better than frequentist approaches? I don't understand why a post probability or posterior probability approach is better. I think what you might be trying to do is take into account something about the sensitivity and specificity of the test for breast cancer in this case. If so, I would love to hear more about that, because that's kind of what we're doing with cognitive tests. So I'll end there.
So let me see if I can restate it. Okay, tell me, what is the payoff here? What do we get from this that a frequentist analysis might not? I think, or the hypothesis is this about sensitivity and specificity that we're trying to incorporate and understand, because that's certainly salient in the world that you operate in. We're going to build to many reasons why Bayesian inference might be advantageous for us, but in the context of this example that we've started, I'd say broadly the core distinction between the Bayesian and frequentist is not the sensitivity and specificity. That's the terms that are in red, the conditional probability of data given the parameters. The core difference is the inclusion of the term in blue, the prior probability. So let me go back to the wording of the problem. Sorry, it's a bit far. There we go. If we read through this, or even in the probability scale, if you say, all right, well, look, I know this. If the patient has breast cancer, the mammogram is going to detect it with probability 0.9. It's not perfect, but it's pretty good. And if the patient doesn't have breast cancer, the mammogram is unlikely to suggest that they do. Great. We get a patient, mammogram screening result is positive. What should we infer? Most of us would say, all right, the patient has cancer. At least that's what the evidence suggests. And indeed, that is what the mammogram result by itself would tell us. That's the evidentiary thrust of that data. The distinctly Bayesian part is to say, factor in the part at the top. Before you observed this data, what did you think? It was super unlikely that this patient actually had cancer. So in this problem for frequentists, it's very tempting to say, oh, a mammogram result is positive. Our estimate is, yes, they have cancer. And that is indeed what, say, a maximum likelihood estimate in this model would be. The Bayesian says, well, you have other information too. You knew beforehand it was super unlikely. Shouldn't you combine? Sorry, I've got a lot to get through. Shouldn't you combine or synthesize those two sources of information and maybe come up with an answer that is a little bit surprising to you, but actually is more properly arrived at?
So can I have a really quick follow-up? So in our case, we're often trying to think about base rates of the disease in our populations. In the clinic, the base rate of dementia is higher than it is in the community. Are you suggesting that our statistics for detection using our cognitive instruments would be better if we take the base rate into account?
Yes.
Paul Mayo said that like 60 years
Yeah.
ago. Paul Mayo.
Yeah, I'm not suggesting that as, I'm not proposing that as a novel thing, but yeah, that's the thrust of this is yes. Yeah.
That was an incredibly helpful question and answer.
Okay.
So I don't know, that maybe I've answered my question, but in the spirit of using terminology that we may be more familiar with. So it's not about sensitivity and specificity, but it's about positive and negative predictive value.
Yeah.
And that's where base rates comes in. That is very helpful.
So sometimes, yes, and to connect the question to one that came up earlier, sometimes I hear frequentists say, well, yeah, this isn't Bayes inference. We do this all the time with base rates and so on. I say, yeah, it's Bayes inference. You're just calling it something else, but it's Bayes inference.
Thank you.
Yeah.
Anyone else?
So I get the feeling we're all getting ahead of you in your, so sorry about that. I'm a big proponent of incorporating prior information, but I think another piece to add to this conversation or bookmark it for later in your talk is that if you have a large sample and you have a lot of current evidence that will override that prior information.
Yep.
Potentially as well.
Yep.
So
We're getting there.
Yeah.
Yeah.
So anyway,
Yeah.
just
Yeah.
put that on the table.
Yeah. So let me introduce another example that will introduce or highlight a lot of some of these principles that are coming up. This is a simple example from my world in educational measurement. We're assessing students' knowledge in some domain. We have a test and the test is score range. We give the test to all the students and we get their scores, and that's my data. The score for the first student, score for the second student, everyone taking my test. And think like Stats 101, inference about the mean of this distribution of test scores, assuming or pretending the variance is known. Let's just keep it simple, focusing on an unknown mean. So here's my model, or here's my Bayesian analysis. I'm going to do the usual thing where I say my data are normally distributed with some mean and variance. I'm pretending I know the variance, and I'd like inference about the unknown mean. It should feel like Stats 101 vibes for us doing this. What does Bayes inference have to say about this? Well, there's Bayes' theorem now for this situation. On the left-hand side in purple is the posterior probability for the unknown parameter. What's the probability distribution for the unknown mean mu given the known stuff, the data x and the known variance sigma squared? And I'm just populating Bayes' theorem on the right-hand side. And if you drop the green thing in the denominator and you're just working with the numerator, what you have is what is proportional to the posterior. It's where the action is. That's where I'm going to focus my attention. There are two terms there, one in red and one in blue. Let's step through them. The term in red is the conditional probability of the data given the parameters. This will also induce a likelihood function for the parameter. This is regular old, our data are normally distributed with some mean and variance. This is what you've probably been doing since those early stats classes. The term in blue is probably what's new. The distinctly Bayesian part, or the part that makes it Bayesian, is this prior distribution. This is a probability distribution for the unknown parameter, here mu, the mean of a normal distribution, that expresses or is intended to express what I think about the situation before I've observed the data in X. And in this context, data are normally distributed with an unknown mean. What prior distribution is commonly used for this unknown mean is also a normal prior distribution, a normal distribution. So my expression there, again, blue stands for stuff in prior distributions. For the unknown mean mu, I'm going to assign it a normal prior distribution that has its own mean and variance. I like to write very long, clunky subscript sometimes. The subscript tells me of what. So here I've got mu sub mu and sigma squared sub mu. That's mean and variance, mu and sigma squared. The subscript says of what? Not of data, but of a parameter mu. That is, these are the mean and variance, not of the distribution of the data, but of the distribution of the prior for the parameter. In certain literature, these are sometimes referred to as hyperparameters. Parameters are the thing that govern the distributions of the data, and then hyperparameters are the parameters that govern the distribution of parameters. Sort of a layering of things. All right, so in my example, just to walk through it, this is the setup we have. I collected, let's see, a set of test scores. I think I had 10 people. First student scored a 91, second student scored an 85, and so on. Those are their 10 test scores. I've gone ahead and calculated the mean of those test scores in the data is 84.1. What were my prior beliefs about the average test score? Well, I'm going to use a normal prior that has a mean of 75 and a variance of 50. I like to look at pictures. There is a normal distribution with a mean of 75 and a variance of 50. Why did I select this? Is that better? No. I didn't touch it.
As long as people on Zoom can hear and people in the back can hear.
Let's see if this one. Switch room next time. Hopefully that's better, different. Yeah, okay, great. So here's my prior distribution for the unknown parameter mu. Why did I specify this distribution? Well, it reflects my beliefs before I see any of the data. I'm about to give this test to my students. What do I think the average test score is going to be? Yeah, my best guess it's in the neighborhood of 75. This distribution, my distribution here, centered at 75. That's my best guess for what I'm going to see. Am I certain of that? No, but I have some beliefs. I think it's pretty likely that the average test score is going to be, I don't know, somewhere between the low 60s up to the upper 80s. I think it's super unlikely the average test score is going to be down below 60 or 50, and it's super unlikely it's going to be way up in the upper 90s or so. These are my beliefs about the situation. This is a distribution that reasonably expresses those beliefs. If I had different beliefs, like they're going to bomb this test, scores are going to be in the 20s and 30s, then I would have a different prior distribution. But these reflect my beliefs about the situation before I've collected the data. Doing Bayes inference, on the right-hand side in red, the conditional probability of data. That's the old familiar stats term. Data are normally distributed with unknown mean. The term in blue is the prior distribution. That's a distinct feature of Bayes inference. What did I think beforehand? And they combine, and we're not going to do the math, but you can do the math to show that the answer, the posterior distribution, is also a normal distribution. So in this situation where data are normally distributed with unknown mean and known variance, the prior distribution for that unknown mean was a normal prior distribution. It turns out the posterior is also a normal distribution. This is what's known as having a conjugate prior relationship. The prior normal, the normal prior is of such a form that it yields a normal posterior. Again, I'm a picture person. I like to see things kind of plotted out. Up there at the top in blue, there's my normal prior distribution. That's what I thought about the unknown parameter before I observed any of the data. The plot in red in the middle is the likelihood function induced by observing the data. What did I say the mean of the 10 test scores was? Like 84.1? Yeah, okay. If I were doing something like maximum likelihood, I would look for the maximum of that red curve, and that would be indeed at 84.1, the observed mean of the data. Sure. And those two combine, the blue and the red, to give me at the bottom the posterior in purple. That's also a normal distribution, and we're not going to step through the formulas in great detail, but there's ways that you can calculate, well, that posterior distribution, what is it? What does its mean? What is its variance? It turns out that that posterior distribution is a normal distribution with mean 83.67 and variance 2.38 in this case. I'm touching things wrong, sorry. What I want to stress is some ideas about Bayes inference here, and these examples let me do that. One is thinking about Bayes as a synthesis of two sources of information. Here's this kind of schematic of what we just did. In blue there is the prior distribution, and the dotted line right there is right at the mean of that blue distribution. In red, that's the likelihood function induced by observing the data, and well, right in the middle of that red distribution, that's the sample mean. And our posterior distribution at the bottom is literally a synthesis, a combination of these two sources. Visually, that means a few things. One is the purple mountain is going to fall in between the blue mountain and the red mountain. It's a combination, it's an averaging of those two. But it is not necessarily an equal combination or an equal weighted synthesis of those two sources of information. In this situation, I've plotted the, let's see, the posterior mean there in purple. Again, I like to get complicated with subscripts. In purple, mu sub x indicates this is the mean of the parameter mu given the data x in the posterior. It's closer to the blue than it is the red. Hopefully we can visualize this. Well, why is that? Well, what this is a situation is where there's not that much information in the data. Maybe it's a small sample size. So as Bayes inference is a synthesis of these two sources, in this case, relatively speaking, there's more information in the prior, relatively speaking, less information coming from the data. So as a synthesis, the combination is a little bit more tugged towards the prior. On the other hand, if we had a lot more information in the data, maybe we got a big sample size, well, a few things would change. In red, our likelihood function is much more peaked, much more sharp. We have much more precision coming through from the data. And so the synthesis of these two, the blue and the red here, now is much more towards the red. Do folks see that visually? This tends to work for me, but I hope it's useful for you as well. Yeah.
Is there a way to incorporate uncertainty about the prior, the quality of
Yes, the question is there a way to incorporate uncertainty about the prior? If you say, well, I don't know, I don't know what my prior mean would be. Could I have additional layering or expression of uncertainty? Indeed, you can, certainly. That gets into hierarchical models where the prior parameters themselves, like that, what did I pick, 75 and 50? You say, well, those are unknown. They will then themselves get a higher order or higher level prior distribution. Yeah. Another feature of Bayes inference that's important for understanding some of its advantages is how we summarize it. Strictly speaking, our answer is a posterior distribution, but most people don't want to talk that way. If you come to me and I do this analysis and they say, what's the unknown mean? And I say the posterior distribution is normal with mean 83.67 and variance 2.38, that's not going to help a lot of folks. Most people want to distill down information or get things they're used to seeing, like in frequentist inference, an estimate, something like a standard error term, something like a confidence interval. And we have analogs of those things in Bayesian inference, or things that could be thought of as analogs. You can, for central tendency and variability, we have things like means and variances, or means and standard deviations. So here in purple plotted is my posterior distribution. This is my answer, and it reflects my beliefs about the unknown parameter. But you want me to boil it down to a number? I'll give you one number, my best summary. You've been summarizing distributions your whole life. Take the mean of that, it's 83.67. That's my single best numerical summary of the situation. I have uncertainty about that. That's captured by the spread of that distribution, captures my uncertainty to some extent. I could express that in the variance as 2.38, or the standard deviation is 1.54. I could do this with an interval as well. We could do things like get 95% credibility intervals. Here's a 95% credibility interval depicted from a normal posterior distribution. Start at the middle and go out to the lower tail and up to the upper tail such that you cut off 95% in the middle. It's also the highest posterior density. So based on my posterior distribution, I could look up the 95%, the values that cut off 95% in the middle is 80.64 to 86.69. So if you want a single number kind of point summary or point estimate, I'll give you the posterior mean. I can give you a range of numbers like an interval. This is enough to kind of articulate what I would call a general approach to Bayesian modeling. What do we do in Bayes inference all the time? I like a three-step approach. It's been advocated by Andy Gelman and colleagues. Step one, model setup. This is often the hard part. Setting up the full probability model, writing down everything you know, all the model specifications. For those of us new to Bayesian inference, a really useful shortcut is write out or set up the model you're used to doing as a frequentist. Write out your equations or your graphs or your however you're used to articulating or expressing models, start there. And then go through and look at in your model, what are all the unknown parameters? What's all the unknown stuff? List that out. And then that tells us these are the things that require prior distributions or prior specifications. That's model setup. Step two is condition on the observed data to calculate the posterior distribution. That's turn the crank of Bayes' theorem. For simple models like the medical diagnosis or the normal distribution ones, we can do the math analytically. For more complicated models, there is no closed form solution. We turn to things like simulation-based estimation. Software to execute it for us. Okay. And here is just that process written out of Bayes' theorem. We've already looked at this. And here it is for now continuous variables. Only thing that changes is instead of summation, we're doing things like integration, which again poses challenges for doing things analytically. We rely on software to execute it for us. So step one, set up the full probability model. Step two, turn the crank of Bayes' theorem. Thank you, modern software, for helping us do that. And then step three is whatever you're used to doing with output from statistical models and software, do that here. Examine the results, re-specify the model, compare competing models, whatever it is you're used to doing. So oftentimes people ask me, as a Bayesian, can I do, and I don't even need to wait for the rest of the sentence. The answer is yes. Whatever you're used to doing, you go ahead and do. Okay. So why Bayes? In a Bayesian analysis, the posterior distribution is our answer, our solution. As we've talked about, a synthesis of two sources of information. Information coming from the data and information coming from the prior. As the information in the data increases, like we get more and more data points, or the prior is more diffuse, more vague, more spread out, more cautious, if you will, then the posterior more closely resembles the likelihood, the information from the data. So it's a synthesis of two sources of information. I think that has some appeal to me. Other things we get from it, we can build in substantive information, subject matter expertise, or past research into our analysis, often in the form of prior specifications. If past research has told you the correlation between these two variables tends to be between 0.4 and 0.6, build that into your analysis of the new data you're collecting. Probability-based reasoning about parameters allows us to express our beliefs probabilistically. You can say what you mean and mean what you say. What do I mean by that? Let me give you a few quick reminders about frequentist inference. Starting with confidence intervals. Confidence intervals are constructed in different ways, but here's a sort of generic representation for simple situations. Start at your point estimate, go out a certain number of standard errors, and boom, there's your, say, 95% confidence interval. Here it is visually, start at your point estimate. Like if I want an inference about a population mean, start at my sample mean, go out, say, 1.96 standard errors, and there's my 95% confidence interval. Not as many people nodding, but I'm guessing we've done this a zillion times in our statistical lives, right? Okay. So for the data that I started, the example that I had of those, 10 students taking my test and the test scores, I went ahead and I got the 95% confidence interval. It's from 78.25 to 89.95. And if you're like me, in your intro stats class, when you first learned about confidence intervals, you said, oh, okay, that means the probability that the parameter mu is in between these two numbers, 78.25 and 89.95, is 0.95. I'm 95% sure, I'm 95% certain that mu is between those two numbers. And if you're like me, your intro stats teacher gave you a metaphorical slap on the wrist and said, no, that's not what a confidence interval tells us. No, it's not where the parameter is likely to be. What's the interpretation of a confidence interval then? Upon repeated sampling, 95% of the confidence intervals constructed in this way will contain the parameter inside them. There's no guarantee that this one will, and we can't even speak probabilistically about this confidence interval. People make this mistake all the time. They get their frequentist confidence interval and say, I'm 95% sure then the parameters between these two numbers. That's not what a frequentist confidence interval allows you to say. What about, yeah?
I'll just try to talk really loud. I don't think I understood that. Can you
Okay.
come back?
Yeah.
What am I supposed to interpret and how is that different?
I yanked out some of the nice visuals on this point, but let me just try to talk through it. So wait a minute, what's going on here? I thought, or what's the difference here in these interpretations? If you're like me and every intro stat student I ever teach, you want to make the interpretation at the top. And a frequentist confidence interval does not allow a probabilistic statement about a parameter. To a frequentist, probability comes from things like repeated long-run stabilizing relative frequencies over repeatable events. So my intro stats teacher drilled this phrase in upon repeated sampling, upon repeated sampling. If we were to repeatedly sample from this population and do the same analysis, the samples would vary, the intervals would vary, but 95% of them would contain the parameter. That does not permit me to talk about this interval that I have with this data set. I wish it were so, but it doesn't allow us to do that. This is very tricky, and this is why people blur or confuse these issues all the time. So I don't know if that clears it up other than to say, oh, wait, we're not supposed to talk like that? No, you're not supposed to talk like that. The frequentist notion of probability is constructed about upon repeated sampling. So it's prospective about what would happen over many repeated samples, not about any one in particular for which you have observed data. Yeah.
Repeat that, right?
Yeah, I'll repeat that, which is that in a frequentist inference, parameters are typically treated as fixed but unknown. I don't know mu, the mean of this distribution, but it is, as was just nicely stated, it is treated as fixed, meaning it does not get a probability distribution, so I can't talk probabilistically about parameters. What, I think that's well stated. What can you say about like these numbers? I leave that to frequentists to try to help you out with. Yeah.
So correct me if I'm wrong, but it seems to me that the big distinction is from a frequentist perspective, you can talk about the probability of the data, assuming your theory is correct. From a Bayesian perspective, you can talk about the probability of your theory, assuming that the data are correct.
That's right. So frequentist inference is built around the probability of data given parameters or hypothesis model, however you want to frame it. And Bayesian inference reverses or allows us to reverse that directionality and talk about the probability of parameters or theories or hypotheses given the data.
So that backwardness in frequentist theory, if you're a Bayesian, shows up in this interpretation.
Yeah, and people make this mistake all the time, interpreting things incorrectly as a frequentist. The inventors of confidence intervals said this. Don't treat this as a probability. It's not. You see, you know where this is going. What does the Bayesian interval allow us to do? Talk probabilistically about the parameters. I can say, I don't know where the parameter is. According to my analysis and my model, there's a 95% probability it's between these two numbers. This is what you've wanted to use all the time, right? This is how you've always wanted to interpret confidence intervals, but your stats teacher slapped you on the wrist, metaphorically. From the literature on how people interpret intervals, Mori et al. Frequentist confidence interval says nothing at all about the probability that a particular observed confidence interval, these two numbers I got from my data, analyzing my data, contains the true value. It is either 0 or 1. Only the Bayesian procedure, yielding posterior credible intervals, allows the interpretation that there is a, say, 95% probability the parameters located in the interval. And from Simon Jackman, adopting an explicitly Bayesian approach would resolve a recurring source of confusion for researchers, letting them say what they mean and mean what they say. Same thing shows up in hypothesis testing. Suppose the p-value for hypothesis test is teeny tiny, 0.02. If you're like me, your first stats class got that p-value 0.02, and you said, the probability that the null is true, like the mean is equal to this number, is 0.02. And your stats teacher slapped you on the wrist and said, no, that's not the meaning of the p-value. The p-value is, if the null hypothesis is true, the probability of seeing a test statistic, some summary of the data that is as or more extreme than what we actually observed, is this value, is this probability. And the distinction I want to draw is that the probability for the model being true or parameter taking on a particular value given the data is not the same thing as the probability for the data given the model or the parameter. People confuse these things and think they're equal all the time. In our medical diagnosis example, if the patient does have breast cancer, the probability of the mammogram being positive is 0.90. We were told that. So it's very tempting to think, well, if somebody has a positive mammogram result, the probability that they have cancer is 0.90. That would be making this mistake. Bayes' theorem is what allows us to reverse the directionality here. Bayes' theorem is what allows us to say, well, if they had cancer, here's the probability of seeing the mammogram result being positive, to reversing it to say, once we've observed the mammogram result, what's the probability that they have cancer? Those two things are not the same. What Bayes' theorem highlights is we need the term in blue. We need the prior distribution. That's what enacts this reversal, looking from the right-hand side. How do you get from the red to the purple? You need the term in blue. Confusion of these, blurring these, is a common mistake. From Cohen, what's wrong with null hypothesis significance testing? Well, among many other things, it does not tell us what we want to know. And we so much want to know what we want to know that out of desperation, we nevertheless believe that it does. What we want to know is, given these data, what is the probability our hypothesis or model is true? But as most of us know, what hypothesis testing tells us is, given the null or model is true, what's the probability of these or more extreme data? These are not the same, as has been pointed out many times over the years. One of my favorite quotes from Jackman, adopting a Bayesian approach resolves a recurring source of confusion for researchers, letting them say what they mean and mean what they say. This is how you've always wanted to, if you're like me, always wanted to talk about your statistical results, but the frequentist said, nope, 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 that's not what it means. So why Bayes? Other reasons. You can work with any aspect of inferential interest. So much of statistics is built around means, variances, and covariances, because mathematically they're easy to work with. Anyone ever work with things like extreme percentiles, skewness statistics? Anyone do hypothesis testing for skewness? No, because the math is hard to do. It's not very commonly done. If you're interested in any feature, you can examine it very easily in a Bayesian approach. It accurately propagates information throughout systems of variables through updating, Bayesian estimate. Bayes allows us to rein in or regularize estimates, avoiding nonsense. Let's say we go out to the basketball court and you see me make 5 free throws in a row. Your data set is 5 attempts, 5 successes. What is the frequentist say my probability of making a free throw is, the estimate? 1.0. I'm perfect, I will never miss. You really think that? Come on. Well, of course not. But that's what a frequentist approach would do. You have prior beliefs that I'm not perfect at making free throws in basketball. Just because the data are suggesting a variance is negative doesn't mean we should think so. Anyone ever run an analysis and the estimate is the variance is negative? Things like Haywood cases and things, yeah. Do you really think that variance is negative? No, you have prior beliefs that would help you avoid such nonsensical conclusions that the frequentist result gives you. Bayes inference also supports the proper accumulation of evidence as data arrive for updating beliefs. Paul very nicely hinted at this earlier this morning. Here's kind of the idea. Starting at the top, for the first data set that I'll call X1, we do Bayes inference. We start with our prior distribution in blue, we get our data in red, combine them through Bayes theorem, that gets us to our posterior distribution that's at the top left. That's after data set 1. Now I have gone and I'm going to go get my next data set. What should my prior beliefs be before analyzing the second data set? What I thought after analyzing the first data set. So the posterior distribution after data set 1 becomes my prior distribution for analyzing data set 2. And then I update my beliefs with data set 2, takes me to a new posterior, which is really just the prior for the next data set. So Bayesians have a saying, today's posterior is just tomorrow's prior. We do this all the time, right? Pilot studies, why don't we just call them different things? You do the pilot study and then you drop that data and you claim to learn things and you sort of formalize it. This is a very natural way for formalizing the incorporation of past knowledge into the present analysis. Hierarchical approaches to model construction allows us to do things like borrow strength about inferences in very complicated ways. A nice example of this comes from election forecasting. Starting in the early 1960s, NBC employed John Tukey and others to make updated forecasts on election night, which is not an easy thing, particularly with 1960s technology. There are various forms of data available on election night. Past voting results by different levels, like by counties, polls leading up to the election, predictions from experts, completed precincts that have rolled in, as well as partial results from the precincts that are not yet completed. And you can use all these different sources of data to construct the model in a hierarchical fashion to build a prior distribution. Do you really need that if you have lots of data from a particular precinct? Not really. The real payoff is that you can leverage that kind of information for places where you have relatively less information. This is the notion of what Tukey called borrowing strength across the hierarchical model. Another example, late 1960s, early 1970s, predicting college GPAs from like admissions test scores. There are hundreds of different colleges. Do you want to build a little regression model for each college? Some of them have very small sample sizes. Do you want to fit one regression model that assumes all colleges are the same? Probably not that either. So a hierarchical approach allows you to build things, allowing for distinctions, but borrowing strength from when there's more information to help you out with where there's less. Yeah, sorry, I missed some hands in the background. Yeah, so the question there is, wait, maybe some of the data you have shouldn't really speak to what you don't have. Yeah, this gets into notions of exchangeability. Exchangeability roughly is the idea of, should we treat these things the same? In perfectly exchangeable situations, like, toy examples like flips of a coin. I don't really think anything differently about the third flip of the coin as the 103rd flip of the coin. to me beforehand, they're roughly exchangeable, I can treat them the same. When we think, wait, these things are not exchangeable, these are different populations, or there's a meaningful difference here, we should not treat them the same. What we need is something more complicated. That usually involves models that have things like covariates. What makes them different? Or in what ways are they different? I'll give you a measurement example from my world. A colleague of mine and I were talking about measuring, doing surveys of firefighters. And they had previously done surveys of police officers. And the measurement quality was like, well, we sort of think they're kind of similar populations with respect to what we were measuring, people who go into service in different ways. But firefighters and police officers are not the same population. So how do we borrow some information from what we learned about how the measure works with police officers to use that as background information for when we go work with the firefighters? They're not fully exchangeable to us, but there's some degree, and we want to try to capture and express that. It just means we need a more complicated model and story of the situation. Yeah.
I also really like the notion of less informative priors / more humility. So you could set up such a model where, yeah, I know something from one population of people, but maybe that's less related to what I'm going to see in this new population of people. So I can play around with the parameters and have the data more readily outweigh.
Yeah. So the question there is, if I suspect the only thing, an advantage is I can sort of taper off some of the emphasis put on this source of prior beliefs and sort of downweight that. Absolutely. Yeah. We're in control of that.
But no, do you mind trying to repeat the question?
Sorry. Yeah. The question was about having the ability and having the ability to have more vague or diffuse, or I would say modest prior specifications. Yeah.
As you know, I tend to favor the relative frequency interpretation. The first example that you gave is a great example of empirical Bayes. The prior distribution is called the prevalence, which is standard term. The posterior probability is called the predictive value of a positive test. And everybody uses that, whether you're Bayesian or non-Bayesian. So there's nothing uniquely Bayesian about that first example. It's simply a matter of using the data. And I think both Bayesians and non-Bayesians have exactly the same approach. The only difference is a label. You call it the posterior distribution. Most people call it the predictive value of a positive test. The last example, the polling example, is rather interesting because I don't see any prior distributions. I see polling results, and we're really interested in the outcome, not what you think the outcome is. What is the outcome? So there's a real parameter there, and it's fixed. Trump gets elected or doesn't get elected. So there is a definite fixed endpoint that we're interested in, not just what I think the endpoint is.
Okay, let me try to restate that and comment. So in the first example on the medical diagnosis, saying that there's a difference in terminology, but that both Bayesians and frequentists would tackle the problem in the same way. I think that was the thrust of it. To which I say, yeah, it's a Bayesian analysis. Bayes has often been thought to be sweeter by any other name. And so it's had lots of different names in different contexts that has been used by others. That's fine. I think a strict frequentist interpretation would not allow for the incorporation of base rates. Sometimes I see frequentists say, yeah, we do it, but it's not really totally what a frequentist ought to do. Or if it is, the inference is not about a particular patient having a probability for the same reasons we talked about with confidence intervals. It would be about a pool or population of patients. It would not allow me to talk about this patient who's just, I've gotten the results for. That's what frequentists have told me. I think, all right, frequentists, you go sort yourselves out and figure it out, how you want to handle it. But if frequentists are doing Bayes inference to do better inference, that's fine with me. Regarding the polling example, I wish I had a whiteboard to kind of diagram it. It's the idea here is about a hierarchical construction where we have different levels, like different counties or different precincts, and we're trying to say, well, what is the vote share going to be for this candidate in this county? Well, our prior might be in some sense formed by, well, how did they vote in the last election? That might be a source of prior information. But we can also draw or borrow strength from neighboring counties. They're not the same, they're not totally exchangeable, and we need to build a model for how they are similar or different, but that can also inform our beliefs about this county, in addition to the data we actually get through election night as the results roll in. This kind of hierarchical approach allows us to model construction and inference, model construction and then inference that borrows strength for inferences about parameters, allows us to work at different levels of multi-level systems, individuals, groups, geographic units, what have you. Bayes also offers a coherent treatment of unknowns. Parameters, functions of those parameters, missing data, latent variables, random, so-called random effects of multi-level models, and so on. Very often we teach and we learn these things as sort of separate topics. Oh, here's a latent variable model, here's what to do. Oh, if you have missing data, here's what you now need to do, and so on. From a Bayesian perspective, it's very coherent to tackle all these kinds of problems in a same sort of way. Bayes also manages and propagates uncertainty due to things like measurement error and other sources. A red flag for me is anytime somebody treats something that is estimated as if it were the known true value. That always gets my the hairs on the back of my neck to stand up and say, wait a minute, do we really know that? Or are we ignoring some uncertainty? Nothing I've said involves asymptotics. At no point have I said this works as sample size gets large. Don't need asymptotics for estimation, uncertainty, evaluating model data fit. Bayes often performs better at small samples. Why do some people do Bayes inference? Some of them do it to do hypothesis testing better. Some people say, I like hypothesis testing. And actually, I think Bayes inference gives me a better way through things like Bayes factors and other sorts of tools to do hypothesis testing better, to quantify the evidence in favor or against a hypothesis better than a frequentist approach. I'm more of a model-oriented person than a hypothesis testing person. So people like me often turn to Bayes inference to do modeling better, even without hypothesis testing. We could do things like build in like utility functions to integrate things with decision-making and so on. And then really lastly, what I'll say about advantages is there's no denying that Bayes often, it seems like more work for simple models. It is. There's more stuff to specify. The software can be difficult to make sense of. It can be more work. But when we want to push the boundaries of our modeling or analysis capabilities, turns out it's often easier to do that with Bayes approaches. I have a number of colleagues who say, Roy, I don't buy any of that Bayes philosophy stuff you're selling, but doing it as a Bayesian allows me to run my analysis and get my job done. Okay. Yeah.
On the previous slide, just to clarify that top point where you say often performs better at small sample sizes, you mean that for small sample sizes, Bayesian probably works better than frequentist, not that you would prefer for a Bayesian analysis to have.
Yeah, that's right. I'll always take more data. Yeah. So the question is, wait, saying it performs better at small sample size is not that Bayes performs better at small than a large sample size. At small sample size, Bayes can often perform better than frequentists. Yes, that's what I'm. Yeah.
Thank you.
Yeah.
I think I'm a little confused about where bias come from necessarily. Like if approach,
Mhm.
am I like going back through like papers to like, just to be very explicit, like let's say I'm looking at like crime data related to memory or something. Am I going back through papers that also look at crime data and memory and finding their like reported statistics and the model that's separate?
Yeah, so the question is a little bit of confusion, or where does the information come from for specifying priors? And to make it concrete, if we're looking at a paper or analysis on crime and memory and how they're related, should I go back into the literature and look at past findings and so on, and then incorporate that in as part of my prior distribution? Abstractly, there are a lot of different sources for prior information. Some is past research that others have done. Things like meta-analyses are terrific for that because they kind of give you a broad overview of past findings. You might have pilot data, like a small pilot data set before the larger study. It could be theory or expert beliefs. There's a whole realm of Bayesian statistics of what's called knowledge elicitation, where you sit down, you as an analyst might sit down with an expert and say, talk to me about this, and we're going to transform your beliefs into these prior distributions. So theory, past data, past findings, and so on. What I'd submit to you is, I'm guessing you do this all the time. It's called a lit review section. And so you have qualitatively gone through past findings, theory, and so on to arrive at various decisions and choices you've made, what predictors to include, what to exclude, what's important, what's not, what other people have found, and so on. You've already done that in many cases. What a Bayesian analysis says, well, don't leave it in the lit review section. Bring it into your analysis of your current data too.
Just one quick follow-up. If I'm wrong, so for example, like I think it's not a positive association, and it's actually reversed, maybe I have like a bias sample or something. Is my like assumption about the prior distribution going to further bias the result?
So the question there is, if your prior is in some sense wrong, wrong may be wrong against the world, or wrong may be discordant with the data, is that going to bias the result? Bayes is the synthesis of two sources of information. And so again, if you see me make 5 free throws in a row, the data tell you I'm perfect. Your prior is that I'm not perfect. Let's just say your prior is that I'm not perfect. Is that wrong? Well, it's a little discordant with the data, but I'd argue that's a pretty good prior to have about me, is that I'm not perfect. So judging whether something is discordant is a little bit different than judging whether it's wrong. We're not going to go into the mathematics of it, but there are ways to show that we could start with very different prior beliefs. I think this person is very likely to make a free throw, and you think they're very unlikely to make a free throw. With more and more data, our beliefs are going to converge. That's called the principle of stable estimation, and so on. That is like, you can start at the wrong place, and if you get enough data, it'll take over. Does that help? Okay. Yes.
This may go off in a more technical direction. We can talk about later. But some further clarification of this first point. No reliance on asymptotics for estimation. We heard about a lot of Bayesian versus. And on the Bayesian side, you're supplying a lot of upfront information in your prior about how things distributed and things like that. There's also language differences, credible intervals versus confidence intervals. So what exactly does that mean? No reliance on asymptotics.
Okay. So the question is clarifying that point. What does it mean, no reliance on asymptotics? I'll say that as a Bayesian, I don't need to supply a lot of information in my prior beliefs. I could have very diffuse, very flat prior, so I'm not actually doing it. So the point holds regardless of how strong my prior beliefs are. If you're like me in statistics class, you learn you get estimates, you get standard errors, you get confidence intervals, you get chi-square goodness of fit tests, and things like that. And tucked along the way in there is, this works asymptotically. The standard error that is estimated for my parameter in my complicated model, it's not a standard error. It's not the standard error. It's the estimated standard error, which works well asymptotically. And my chi-square statistic is not actually distributed as a chi-square. It is asymptotically distributed as a chi-square, usually as sample size gets bigger. As sample size gets bigger, these things behave this way. All your likelihood ratio tests, many of your confidence intervals are warranted under asymptotics, large sample sizes. How large is large enough? I don't know. We derive, a lot of frequentist machinery derives, this works asymptotically, as sample size goes to infinity. Let's hope it's good enough for our finite sample size. We don't need any of that in Bayes. Bayes theorem works the same regardless of your sample size. The posterior distribution is arrived at in the same way. For model fit, I've done a lot of my work in model fit in my career. I say things like, this thing is like a chi-square statistic for evaluating goodness of fit asymptotically. I don't need to do that with Bayesian model fit. Does that help? Get it?
Is that a function of the way things are estimated? I mean, underlying CLC estimation, how that works?
You don't need them. I think the connection is the derivation of sampling distributions in, like, say, maximum likelihood estimation, which is elegant and beautiful, but is often justified only asymptotically. The math is such that, yeah, this thing will be this will be a good standard error estimate, or this will be a good confidence interval, or this will be a good test statistic as sample size goes to infinity in order to make the math work. Bayes theorem, don't need that. Yeah.
Just to be clear, with the posterior is incorporating the sample size in the data in your red bar, right?
Yeah, to be clear, the posterior incorporates, I would say, the information in the data. Crank up the sample size, the data are going to contribute more. Yeah.
So in the prior, how do I weight how much sample size was in that prior? My prior may have been based on 10 million people, so I might have a sample size of 10,000. That's really cool, but against 10 million, that's a strong prior.
Yeah, you might have, there are ways to express different amounts of, I would say, strength or certainty in the prior. Some of them have nice metaphors as like, well, this prior strength is as if I observed it on 10,000 data points. Wow, that's really strong. So for some priors, it's less easy to use that metaphor, but it's a useful one if you can. So I'm sorry, I may have missed the question, but so how do you do that is the question?
Yeah. Does the model incorporate the strength of the prior?
Yeah, does the model, yes, it is does the model incorporate the strength of the prior? Yes, if I am really, really certain that this player is not perfect and will miss a free throw eventually, then it doesn't matter what the data are. If I'm really sure of that beforehand, that's going to be factored into the posterior. Yeah.
I have several different clients I want to use. Is there a way I can check which one is the best and the most reasonable one, or should I somehow combine all of them?
Yeah, so the question is, if I have different background information, I might have several different candidate priors. Is there a way to check which ones are kind of better, or do I have to pick, or could I combine them? And the answer is yes to all those things as possibilities. Then there are some scholars who say that's actually great practice, that it's called a sensitivity analysis. Say, whatever you're doing, think about an alternative prior structure and run the analysis with that, see how sensitive your conclusions are to different specifications. There are ways to, through what are sometimes called model averaging or hierarchical approaches, synthesize across multiple priors. There are kind of analyses I suggested about prior data discordance to see, all right, is there a real conflict here between this prior and what these data have to say? Not necessarily meaning one is right or wrong, but just to characterize that. There are all these sorts of tools and techniques that you can do. Yeah.
Like say if you're, because when the sample size is very small, whole theory is more close to the probably one sample size is much larger. to the background. I know when the sample size is infinite, that it don't count.
Yeah, so the question is if at the beginning when there's not much data, the posterior closely resembles the prior. And the more and more data you have, the more the posterior will resemble the likelihood. Indeed, that's the case. This will try to kind of in a toy way illustrate that here. On this slide, relatively speaking, more information is coming from the prior. On this slide, relatively more information is coming from the data. If we look at where the purple posterior is, in one case, it's much closer to the prior, and in the next case, it's much closer to the data. In the limit, as you get infinite data, the prior becomes irrelevant. Yeah, and the likelihood dominates the posterior. As it makes sense, right? Get more data, the data ought to drive the solution more. It'd be weird otherwise. So, and that's indeed how Bayes' theorem works out. You're not free of me yet, but let me close this portion with just some final words. I like this from paper by Box. This is from 40 years ago. These days, the statistician is often asked such questions as, are you a Bayesian? Are you a frequentist? Are you a data analyst? Are you a designer of experiments? I would argue the appropriate answer to all these questions can be, and preferably should be, yes. So this is about incorporating tools into your toolkit. I don't necessarily expect that people new to Bayesian inference will say, well, let me get rid of all that frequentist machinery I've learned and come over to Bayes inference wholly. The idea is to recognize that it's a tool that may be advantageous to have in your toolkit. And then the final words I have for this, I was fortunate enough to co-write a book on Bayesian psychometric models. And this is literally the end of our book. Our model is a story, not only of the world as we understand it, but aimed at affecting a certain outcome, facilitating inferences we would like to make. Regardless of the statistical framework we adopt, we strive to get our story straight, aimed at what we desire to reason about, reflecting our beliefs, purposes, and constraints. Bayesian approaches to, I would say, modeling, but in this case, we're talking about psychometric modeling, serve us in two ways. They enable us to tell better stories and provide us better ways to tell them. So that's the thought that I'd leave you with. I think. So that was great. The next part's shorter, I promise.
Well, great. And I think people need a break and there's lunch in here anyway. So what I'm proposing that we do, and I'm organizing this so I get to dictate what we're gonna do. We're gonna stop here.
You are free of me.
Yes, for the
All
moment.
right.
And then lunch will be an hour, but then let's come back right at 1 instead of 1:30.
Okay.
We built in a half-hour break after lunch, so we'll come right back here at 1, and then you can.
Terrific.
And that was, I think it was really important that we have a good interaction, opportunity to ask questions and answer them. So I'm
Sounds good.
totally happy with this. So this is a great session. Thank you all for your terrific attention. Thank you, Roy, for a really nice intro to these topics. And we'll see you all at 1 o'clock.